right, we're going to start on the hour, so people can walk in. Hey everyone, thanks for coming to this session. My name is Andreas Fredriksson. I'm a principal engineer at Unity, and I manage the Burst compiler team. And this talk is going to be about what we're doing. It's a sneak peek in what we're doing with enabling more low-level engine kind development with Burst. So who is this talk for? To check if you're in the right room. You care about CPU performance. You're in the right room. Maybe you have some existing high-performance code, like maybe some engine modules written in some other engine or in Unity as native plugins. Maybe you have some really core simulation logic that you want to port to HPC#. This is the talk for you. Maybe you just go to technical talks because they're cool. Hey, I do that. You're in the right room. If none of these points apply, maybe you want to go get coffee. So here's what I'm going to cover today. I'm going to, for the benefit, not everyone is like a engine programmer SIMD nerd, like me maybe. So I'll give you a quick introduction to SIMD and what matters. We're going to go through the options you have today, right, to get SIMD code out of HPC#. And we'll look at what we're doing with Intrinsics and Typeless SIMD. And we'll look at some use cases, and then hopefully we'll have time for Q&A. So with that, as I promised, I will give a little background to SIMD. So what is SIMD programming? If you haven't heard about this, the acronym stands for Single Instruction Multiple Data, right? So you're doing more than one thing at a time. Cool, that's it. The thing is, this is not some esoteric thing that you have to get an accelerator card or something for. Like every single phone, every single computer in this room has SIMD hardware on it. And it matters. It's a big deal. So obviously, on mobile devices, you have access to AR64 and Neon. And on desktop platforms and consoles, you have available to you SSE and AVX. All right, so the first thing is, to get it, like, that sounds all very abstract, right? But you can understand this easily if you think about cooking. So prepping a salad for your dinner guests. You have your input data here, illustrated as multiple independent pieces of celery stalk. And you have your instruction, right? And each move of the knife, one instruction, is going to cut more than one independent piece of celery, which then gives you your output data, right? You're accomplishing more in a shorter amount of time. So this looks silly maybe, and you're like, who's this guy? Like, why is he using cooking analogies? There's one important thing I want to call out from this slide. One of the few things I hope you take away from this talk is that in order to get the benefit of quicker chopping, you have to do some upfront work, right? You have to take your stalks of celery and lay them out in a particular way so you can use this pattern, right? If you have dinner guests waiting for their salad and you decide to go like celery stalk by celery stalk, they're going to get hungry and angry, and think of those as your players. So why is all this important? Well, obviously it's more efficient, just like in the cooking example, to do more things with fewer instructions. But the point really, right, and I sometimes get maybe too passionate about this, but there's dedicated hardware for this stuff that we don't want to be ignoring. And one other point I will bring up here, which may be news to some of you, is that using SIMD instructions is often the only way you can get the maximum cache bandwidth of a particular CPU. So if we start with that first point about dedicated hardware. So this is for illustration, right? This is a block diagram of an Intel Skylake microarchitecture CPU. And I'll bounce a little square for you here to draw your attention. This is a dedicated block of many wide lane implementations of SIMD hardware. Like it's SIMD ALU. If you're not using these instructions, like you're not using what the chip can do. So I mentioned cache bandwidth. So what am I talking about here? I'm not talking about the sizes of the cache lines. I'm not talking about hitting cache or all those things. All those things are good to know. What I'm talking about here is a different thing. So if you're reading from the cache and you hit in the cache will be able to deliver n bits to you every cycle, mostly, right? And the thing to realize is that this n is typically much, much bigger than what you can fit into a scalar variable. Even if you use a 64-bit variable like a ulong or something in C#, right? The cache could give you at least twice that amount of data per cycle. So 128 or 256-bit cache buses are common. And my point then is, if you're using scalar instructions, you're throwing half of that away. So if we look at an illustrated example here, well, not illustrated, but a specific example. So the first thing I want to preface this with is, this matters when you're in cache, right? Which we hope to be most of the time, right? So if you're already processing data in a fashion that's efficient for the cache, then this starts to matter a lot. And DOTS and ECS is all about laying that data out for you, so you're much more likely to be in cache, and this starts to matter even more. So let's say that you're processing floats, right? You have some cloth sim, or maybe you have some, I don't know, some other cool thing. And you're processing floats, right? Floats are 32 bits, 4 bytes. And so every time you read and hit the cache and get a float back, you could have been getting 3 more, right? Because you're only using a quarter of the cache bus. So a better mindset then, if you're targeting a device with 128-bit cache bus, is to say, oh, I should be processing 4 floats at once, right? Because every cache hit gives you the maximum throughput of the cache back. Also, I want to preface everything we're going to talk about in this talk with a common fallacy or misconception, right? We talk about vectorization, we talk about vectors of stuff. Now, it's important to realize that these are mostly unrelated to the mathematical concept of a vector, right? And a lot of people are confused by this because we tend to bend these words around, and we tend to, look at examples where someone is using a 3D or a 4D mathematical vector to do things. So the first myth I want to bust is that because you're using a vector math library or a vector type, right, that it's somehow related to SIMD. It's not. They're orthogonal concepts. What is true, however, is that when you're working with arrays of data, and many SIMD sort of aware math libraries will try to make this true, when you're working with groups of data, that can lead to opportunities for SIMD programming, but it's not always true. So I'll show an example next. This is especially problematic when you have a mismatch with the unit of work that you have, say, a 3-wide vector and the hardware. So before we get into the examples, though, I want to give you, if you're not super familiar with like reading x86 disassembly, I'm going to give you my quick smell test for float SIMD-ness for x86. Okay, so if you see something PS, an instruction like that, that's an instruction that works on packed singles. So it is a SIMD operation. And if you see such instructions feeding into each other without a lot of intervening noise, it's probably SIMD code. Great. If you see an instruction that ends with SS, that stands for scalar single, right? It's a scalar instruction that just happens to use 1 lane of a register. Okay, so the other thing you're going to see is a bunch of PS instructions with a bunch of other junk in between them, infrastructure or shuffles, and this is typically a red flag, right? You have some things that are trying to go horizontally in the register, and you have some things that are just, doing something else. Okay, so I mentioned float trees. Let's get to a concrete example here. So in this example, I have a function, static function, that takes 2 float 3s, right, from the Unity.Mathematics library, and I'm computing the dot product. Great. So what do we get out of this? Well, we can use our smell test detector to tell us what we should think about this code. Is it SIMD? Is it not? Okay, so the first thing we see is that we have a multiply, which is indeed SIMD, right? But we only have 3 lanes valid because float 3 is only 3 components. So sure, we get those 3 multiplies with 1 instruction, and 1 lane is just hanging around. And then we have a shuffle, and we have a scalar addition, we have a shuffle, and we have a scalar addition. So what does this all mean if you do the math? It means that we have 1 SIMD operation, sort of. Only 3 out of 4 lanes were active. We have 2 infrastructure ops and 2 scalar ops. And for all that work, we got 1 dot product, right? But hold on, like what's a dot product? Well, it's component-wise multiply of the components and then a sum of those products. So for 3D, you've got AX times BX, you've got AY plus BY, AZ times BZ, and then you add them together, right? That's what we're trying to do. So what I would encourage you to do in cases like this is to go back to basics and express that. So let's do that. So if we write it all out and we get rid of this float 3, which is a horizontal abstraction, And you see the formula there on the slide, which is in fact what I copied to put on the previous slide. If you look at the code gen that comes out of something like this, and we again apply the smell test detector, yes, we see that these are scalar operations, right? And they pretty much map what you have there in the code, right? You have 3 multiplies and 2 adds, which is exactly what goes into that expression. So why is that different? Well, you see that this has no cross-vertical mismatching. It's doing what you expect that it would do. So we have no SIMD ops, no infrastructure, and 5 scalar ops, right? Just like you would have in C or whatever back in the day. Okay, so here's where it gets mind-bending. Now we convert all of those single values to 4 independent values, right? We have 4 independent x's, 4 independent y's, 4 independent z's for A, and the same thing for B, right? The expression is the same. How is this different? It's essentially the same sequence of operations, but they're now doing 4 things at once. So in this case, we have 5 SIMD operations, no infrastructure, and no scalar operations, and we've computed 4 independent dot products, right? This is what you're looking for. This is the mindset that you should be looking for when you're saying, is my code running efficiently on the hardware? So let's talk about that mindset for a bit. The most important thing, I think, when you're approaching this sort of space and you want to maximize the performance is to not get stuck thinking about abstractions, right? And I know it's difficult. As programmers, as engineers, like we're trained to sort of like solve a problem once and then put it away, right? We never want to open that box again because that was sort of difficult to do. But these abstractions carry a cost, right? They carry a cost that you can't really figure out because they're tied to do a certain thing, right? It's not an abstract idea. It also comes with a certain type of behavior. So the most common culprit is thinking about float 3 or float 4 in Unity.Mathematics land as a 3D or 4D mathematical vector, right? Because that doesn't lead to code that vectorizes well in all cases. So the better way to think about it is, great, I'm going to target, say, this ARM device. I'm going to target x86 or maybe PlayStation 4. Well, I know that the vector units on the CPU that I'm targeting runs at 128 bits, and that's 4 floats. Great. What does that mean for my algorithm? So once you're in that mindset, you can start getting used to the idea that, you know, a vector register has a certain number of bits, and you can divide that into whatever width you find convenient to do stuff, right? What can you put in 128 bits? Well, you can put 16 bytes in there. That's pretty cool for a lot of algorithms, like if you're mixing colors and stuff. You can put 8 shorts, 4 floats, 2 doubles, if you really want to go there. Right, and the key point, I hope if you take away one thing, it's this, right? You're looking for opportunities to compute independent values, right? 4 independent dot products, 4 independent force vectors, whatever it is. That's going to give you the best possible chance of getting SIMD code. And like I said, really fight that urge to think of vectors as horizontal values, right? Whenever you find that you have independent components of data laid out horizontally in a register, right? So the X, Y, Z values go together in the register, it's almost always a mistake. Not always, but it can be. And typically you'll find that if you break apart those abstractions and actually swim through them and see what's going on in here, and then lift them all the way up and try to express them using multiple independent components, it's going to be much easier to get the compiler to generate SIMD code for you. Now, I'm not saying you shouldn't use abstractions. That's not why I'm up here, right? What I'm talking about here is when you're down-coding a system that's already been tested and you want to maximize the performance for production. Like you already know the thing does what you want, great. Use abstractions, use float 3 or whatever is convenient to develop that thing, right? But when you're looking to make it 10 times faster, that's when you take whatever you have and rename that to the reference version, and then you down-code a version that runs well on the particular target you're going for. Okay, so how do you do that? How do you get SIMD code? Well, up until when we released the Intrinsics, which we're also going to talk about in this talk, right? You've had 2 options available to you. So you can use, rely on basically the auto-vectorization that we offer through LLVM's auto-vectorization path, or you can write explicit SIMD using mathematics, like in the example that I showed previously. So let's talk about the auto vectorizer for a bit. This is simple mode, or easy mode, right? You essentially target it with your regular scalar code, something, something, magic, magic, and you get SIMD out the other end. And here's one thing I'll say. If you have simple loops that are doing basic, simple stuff with arrays, excuse me, LLVM is often able to just, knock it out of the park. But, it's naive to think that it will do amazing things with everything, right? So if you're banking on this to happen, here's some things that you need to keep in mind, right? You have to make sure that things don't alias, right? If you have arrays that overlap each other in memory or things like this, the vectorizer will be like, oh, I don't know about this. Your data has to be contiguous in memory, right? So that the compiler can convert a scalar load into a wide load. The data has to actually be there. You want to make sure you're using either integers, or if you're using floats, you have to enable fast math options, right? And the reason for this is that floating point arithmetic doesn't follow the same rules as integer arithmetic. So you have to let the compiler break those rules in order to generate SIMD code in many cases. You want to make sure that you don't litter your loops with branches. And, there's all these rules. The pros, of course, is that when it works, it's nice, right? You write scalar code, and at face value, that's more approachable. The cool part about this, I think, is that you can get speedups where you didn't expect them to happen, right? So I'll show a couple of examples here. It also comes with a long list of cons, right? You do need to learn some of these rules in order to say that that will vectorize, right? It's a tool. Compilers are not magic, they're just tools. And this one is, it's great at doing certain things and really poor at doing other things. More importantly, like if you're in a CTO or lead programmer position and you're worrying about keeping your production in frame, and you have a junior gameplay programmer who's enthusiastic and changes something, it's like, who knows what's still vectorized? And so there's no way to tell you that this isn't true anymore. And we're looking at options for how to do that. Like, so you can look at something and eyeball the code and say, okay, tell me if this ever regresses so that, that junior gameplay programmer doesn't check stuff in that breaks that. But we don't have that yet. The other 2 points that I think are problematic with this is that it's frustrating to try to reinterpret data types, which I'll cover later in the talk. And it's pretty often you'll be surprised about what doesn't vectorize. So let me show you a super simple job here. It was the simplest one that I can find that would have a problem if you change it. Right, so I have a simple job. I have an input array and an output array. Right, and in the execute method, all I'm doing is, with the branch that I said you shouldn't do, but in this case, LLVM is able to figure it out. So if an integer is positive, right, greater than 0, we copy it out, and otherwise we replace that with a 0. So it's basically like a clamp operation. And LLVM goes to town. Like this is, 8-wide AVX, 8-way or 4-way unroll, so it's doing 32 per loop. And that's good code gen. Okay, it's Thursday, the day before the publisher build, and you're like, cool, we've got all our shit in order. Junior gameplay programmer is like, we really need to multiply that number by 2. Right, and we are back into completely scalar code. This doesn't even use the SIMD lanes, right? This is going to run at, 1/10 of the performance. If that's some inventory code that's executed like once in a blue moon, you probably don't care. If that's your core simulation loop for the fluid sim that your whole game is based on, you're going to be there all night trying to figure out what happened, right? So that's why for core loops where you're really banking on the performance, we want you to be explicit about what you want, right? So if you are using types like float4 and int4 vertically, like I've showed you here in the dot product example, nothing's going to take away the vectorization from you. It's going to be vector code. And the reason this is true is that these types in the back end, like they don't actually exist as types inside of Burst. These are hardwired into the LLVM IR as vector types. So whatever you do with them, it's just going to use vector instructions. So the checklist here is a little smaller, right? You have to be familiar with a couple of idioms, like, well, how do I simulate a branch if I have more than one thing going on? Well, you have to use selects and masks, right? If you use native arrays, which you should, you can now, from 19.3, you can use reinterpret loads and stores. And these allow you to keep the interface to the job the same. So if you have a gameplay-facing system that exposes, say, a native array of float or a native array of int, you can now load and store much wider blocks from that array inside of your core compute loops. So you can say, reinterpret load this as an int4. And finally, because you're doing more than one thing at a time, you have to handle those cases where you run off the end of the loop because it's only 3. And that's handy then to call out to your reference code that you still have lying around. I don't expect you to read all this code, but I want to show that we're using these sort of patterns with explicit SIMD in things like the megacity. So we developed the hybrid render culling, for example, using these idioms. So in this code, right, there are swizzled 4 wide planes coming in, and we're doing AABB culling against those. And you can see some of the same idioms here. We're doing 4 independent dot products at once. We're doing 4 individual increments at once, and things like this. Okay, so that's the story so far. So why would you need anything else? Well, the first one that comes to mind is Typeless SIMD. In an engine space or like in a low-level space, like these types just get in the way. They are not actually what the hardware does. It's not like it has different instructions for signed or unsigned integers. Like, it's just silly. It really bites you when you're trying to reinterpret data, right? And so a common way that we try to reinterpret data is like we try to pick apart a float or treat it as an int or something. So I'll show an example of that. Sometimes you really want to squeeze out the last bit of performance for a particular target by selecting an instruction that it's exceptionally well suited to do. So we'll talk about that too. And finally, there's a lot of tricks that compilers just will never use because they're not safe or whatever. So let's start with reinterpretation. So I mentioned treating floats as ints, right? And you've probably seen examples of this, or maybe you've written some yourself, and it's not that dangerous, like once you get into it. So here's an example. Like if you're not familiar with this technique, I'll show you this example. This is called the magic float trick. And so essentially this trick is based on the representation of IEEE floating point numbers. So when you take the number 2 to the 23rd power and put it into a float, that is the magic float at which floats no longer have any fractional precision, right? There are no decimals at all in there. So if you take that number, which is OX4B000 in hex, the mantissa lying at the lower 23 bits, if you stick a short number in there, like a U short, and then treat that whole thing as a float and subtract away 2 to the 23rd power, or 8.388 million, you end up with that number converted to a float. And it's really fun to realize that this happens without you using the hardware on the chip that does int to float conversion. And so this has, it has some advantages on microarchitectures where you can break this up and you can say, you have lower latency chains or whatever. And you can also work at different widths and stuff like that. You can do half conversions the same way. I mentioned instruction selection, right? On a lot of chips, there are esoteric instructions that do a quirky thing really well, right? This is an Intel instruction, for example, here, PMOL HRS, which does essentially fixed point multiplication and rounding. And it's crazy fast. Like, if you're trying to do this outside of using this instruction, like, you'll be paying 4 times as much for it. And so I've used this in shipping code in both Sunset Overdrive and Spider-Man. We use this for decal reprojection inside of like fixed point models. And it's like a night and day difference. Using this instruction is like 3 times faster. So if you're looking for something like that, Intrinsics is the only thing that enables you to do it. And so the final reason why you really want to jump into Intrinsics in certain cases is that, compilers are just tools, and, tool in both senses of the word, right? So if you know that you have a float and you know that you don't care about nans because it just came from something where you didn't produce any nans and you want to make a mask of either all ones or all zeros, great. We know that the signed bit is the top bit of the floating point number, so how about we treat it as a signed integer and right shift it 31 bits, right? This is something that takes a cycle to do. And if you do, you have computed that mask without invoking a compare instruction, which has 3 times the latency. So that leads us into what we're doing, and you have some of the background of why we're doing it. So we're working on exactly that. We're going to give you a typeless SIMD library with intrinsic functions. First out the gate is going to be x86, and we're going to add ARM intrinsics afterwards. But we're not just tossing you some native library and saying, hey, go do this, right? This is an actual member of the C# ecosystem. We're going to have managed debugging of it, so if you disable burst, you can still debug this. So I'll show you how it works. I keep harping on about typeless, and you've seen in some of these examples that the types are just an annoyance. Like you have to say, oh no, really, reinterpret this as the other thing, and it's just a bunch of noise. We've seen the reinterpret examples. One canonical example that I want to bring up is comparisons. So if you're not familiar with this, but if you run a comparison, right, you don't set the carry flag so you can branch on it because you're doing more than one comparison. So instead, what SIMD hardware does, it gives you mask back. So it's 0 for the lanes where the comparison didn't pass, and it's all 1s for the lanes where it passed. Great. What's the type of that, right? If I'm comparing floating point numbers, well, and this is where libraries try to, they come up with this problem and they're like, I think it's float, but all 1s is not a valid float. So what we're going to do for this level of abstraction is just do what the hardware does. Essentially, there is no abstraction. And you have 2 core types to work with. M128, which is 128 bits, basically a SIMD register. Right? And M256 for 256-bit targets is going to be your 256-bit register target. And obviously then, the instructions that you choose to use are going to determine how the data in those registers are interpreted. So it's pretty simple to use from a C# point of view, right? You can pull in all the intrinsics for x86 using something like this, or I guess you can type them out with the whole thing if you're a masochist. And then, you do your thing, right? And it's all just using register types. But, it's not that we don't care about C#, like you get full autodocs and this sort of stuff, right? And it's actually meaningful. In fact, this is the nicest SIMD programming environment I've actually been in. It's way nicer than C, because you get actual docs and you can reload the code and look at it in the inspector without taking down the editor, and it's nice. On the user-facing side of the API, right, this is what you'll see if you go look at the code that we have in there when we drop it out. So what's funky here is that there's actually this, which is a reference implementation of what that intrinsic does. So we need that because when you're debugging, you typically disable burst compile, right? So you can use your regular managed debugger. And that means that we've spent a lot of time making reference implementations of these intrinsics that for the vast majority of time are going to be bitwise exactly what the hardware does, right? So you shouldn't be too confused. And they're also handy, if you need to look up how some instruction works, because we've unit tested them all against the hardware. Okay, so I want to give you one more complete example of going through the whole pipe here. So this is an example from a GDC talk I gave a few years ago, which is about Star Trek doors, basically. You're familiar with them, you walk up to them and they open. So to determine if something is in front of the door, we need a radius, and we need some player. And if the player is of the right team, and they step into the thing, then we should open the door, right? And it's a typical sort of testing problem that shows up in gameplay all the time, right? So in pseudocode, what we're trying to do is for each door, we're going to say it shouldn't be open, and we're going to loop through all the players, and if the player is in range and of the correct team, then we're going to set the door to be open. Right? And that is our responsibility. And later down the line, there's some animation thing that does some fancy stuff. Great. So, traditionally, in the engine and gameplay space, these sort of n-squared problems where you're testing 2 ranges or sets against each other, they're the kind of thing that we're ooh, instinctively, we don't want to do that, right? But let's go with it. So we have doors. And here I've just written down naively what they are, oh, I have a position, I have a pre-squared radius, and I have a team. Great. And then I have these test positions, which are derived from the things that can open doors, so I guess players. Or maybe you have droids that can open doors, I don't know. They have a position and a team. So, this is basically just a transcribation of the algorithm you saw, the Python-esque pseudocode, right? So there are two loops nested, which is why it's an n-squared complexity problem. So you have your doors, we're looping through them, and for each door we loop through all the test positions to see, is anyone in front? And the thing I want to call out here is that there's an early out in the loop, right? As soon as we find someone in front of the door, we break out of the loop, right? And finally, we write the results to some array. Great, so here's what LLVM or burst and LLVM will spit out in this case. So we can refer back to our smell test. And we can see that this is, while there are some packed single operations in here, there's also plenty of scalar math, right? So it wasn't able to vectorize this loop. Also, and what's worse is, there's a branch in here, right? So that test that we wrote, or one of them, actually resulted in a branch instruction. It's true that computers are getting better at branching, but they're still extremely slow when they're unpredictable. And the whole thing here is unpredictable. So the first thing we need to do is get rid of that branch. And if you look at the loop here, what I've done, I've got rid of that break, right? And instead, I've combined these two conditions. So I'm saying, is this player in the radius of the door? And does the team match? Right, and then accumulating whether this was true for any player for this door, right, by doing a or equals onto the should open thing, right? And this does mean that we're going to go through all the doors, but remember, that's the worst case anyway, and they are going to be in cache. So we do that, and we end up with this disassembly instead. So the top section, the compute section, is still exactly the same because we haven't changed it. But if you look down here, the loop condition is now handled branchlessly. So there's just one loop, which is what you want to see before you even get to SIMD. All right, so we're going to do explicit SIMD with Unity.Mathematics. So, remember that cutting board and those stalks of celery? Well, the doors are the celery in this case. So we're going to slice it up, and we're going to do break down the float 3 abstraction. And instead, we're going to store x's, y's, and z's in separate float 4s, because that's the width that I'm targeting. I'm going to store my radii squared in float 4 as well, and my 4 teams in an int4. And that's really the only input data that changes here. So here's what that loop looks like, which should be unsurprising, right? It's just that the math has been unrolled. Like I had to put the range comparison, which, is almost a dot product. I had to write that, but, it wasn't very difficult. I want to call out the tests here, right? So you saw in the previous example, when I got rid of the branches, we had a bool sort of accumulator, right? And when you're using Unity.Mathematics, you can use bool 4. And this is a type that we hardwire down to the LLVM I1 vector you get back from comparisons and stuff. So it's basically the same sort of tests, but it's now testing 4 at the same time, and it's accumulating 4 independent values at the same time. And what kind of code gen do we get out of this? We get something pretty awesome. Like this is, if we do the smell test again, you can see that there are broadcast instructions here that are scalar because they're loading one attribute from the player array, and the rest of it is fully SIMD. And this is very nice. Like this will run at least 4 times faster. And the final version of this I want to show you is the explicit intrinsics using, the explicit version using intrinsics. So basically for this, it's silly. You probably wouldn't do this in gameplay code, but it's because we're now familiar with the example, I thought I'd show it. So basically you change all of this to M128s. And, the loop is much the same, except that here you are responsible for choosing the instructions, right? So here we see sub PS, we see mul PS, there's add PS, compare less or equal PS, et cetera, right? Which is, gives you the control to do the thing that you want to do, like we've been talking about in this talk. And finally, I end with a reinterpret store that just stores out the whole block of data to the output array. And what does the code look like? It looks amazing, like you would hope. So to wrap this talk up, I want to give you some guidelines. When you go home and try to really get some SIMD for burst, become familiar with the inspector. We know that it's not the most awesome GUI tool on the planet, but it is a wealth of information for this kind of stuff, right? And with even if you're not an assembly expert, like just using simple tricks like the smell test that I showed you, you can start to get familiar with, what would actually be the performance of this loop. Like we showed here, you really want to get rid of branches in your core loops, especially for engine systems. And as you get into this space, you want to look to increase the sizes of your input batches, right? One at a time should not be the default in code like this. If you use Unity.Mathematics, and you should in burst code, you try to use it vertically, right? So that you have like components for independent values in your registers. And when we drop the Intrinsics package, of course, that's going to give you the least surprises. Like if you downcode to that, you're basically doing a high-level assembly representation, but it also requires the most effort. Some of you may have heard about System.Numerics. They have like a vector thing going on, and like, why didn't we use that? We might consider supporting that API. It's only in .NET Core 3, I think. Right now, though, what we want is to provide an easy porting target for existing engine code, both at Unity and, like guys like you have. And we want to be able to give a really easy transition path. And if you think about it, that's similar to the approach we took with the HLSL syntax that we use in mathematics. And we were able to port things like, GPU, random noise functions, and whatever to mathematics really easily. So to sum things up, Intrinsics are coming. I can't give you a date yet if you're itching to go, but it'll be a few months. Be careful with abstractions, because they always cost something. Adopt a mindset, and once you have that mindset, you'll get better results both from the auto-vectorizer and from our mathematics package. And the key thing to get into that mindset is to think of independent values. Like I said, get familiar with the inspector and go forth and compute things more quickly. And that's the end of my prepared talk. We have a little time for questions. Thank you. I think there are microphones set up in the back. Is that right? Sorry, there are microphones somewhere in this space, so we can do a brute force linear search. So the question is, with the junior gameplay programmer example who broke the vectorization one day before release, like, couldn't we do that? Like, I guess you're exploring, like, what are some ways that we could trap that and make sure that it doesn't happen? So LLVM has pretty good feedback from the loop vectorizer when it says, like, I couldn't vectorize this, or I gave up, or like, life is too hard, I'm going to lie down, or whatever. And so, in fact, they're hidden away in one of the tabs in the inspector today, but I think what we need to do is wire them up, and optionally for you, via an attribute, say, if you ever see this, it's an error. Right? Because then that junior gameplay programmer would be stuck in CI, like he can't land his patch because he just broke vectorization of a job. So that would be one way to do it. And I'm sure there are other ways, so I'm happy to collaborate on other ideas that you guys have. Right, okay, so the addendum to that question is, if you're in that situation already, because they checked in anyway, right, how do you get back to something that vectorizes? Yeah, that's difficult, right? It's like, how do you find a needle in a haystack? But as you get more familiar with the loop vectorizer and LLVM, you'll tend to get a feeling for what it likes and what it doesn't like. So if you're the kind of person who would get assigned these bugs all the time, you would be like, yes, you would develop sort of like an intuition for it. And I will say in this space too, it's really handy if you go on Godbolt. It can accept LLVM IR. So if you copy the LLVM IR from burst, it will actually compile just fine in there, and then you can play with LLVM IR on that level. Or in the inspector, right, you can just play with the C# code and see what happens. And read those LLVM diagnostics. Often the diagnostics will tell you, like, I couldn't vectorize this because there was a hazard. Or like, I didn't think that it was worth vectorizing this. Like, well, thanks, compiler. So I synthesized this code, which is 10 times slower. And that's we have some ideas about how to improve the loop vectorizer, and we're collaborating with a few teams at different companies. But you know, this is sort of like one of the big unsolved problems in computer science, right? And so I guess that is one of the takeaways of this talk, is that you can push ahead a lot if you know what you want to get, like, and you try to write a more explicit sort of HLSL style SIMD instead. Other questions? Yes?
Thank you, very interesting talk. My question is,
Sure. So the question is, you know, now that we have the ECS, you know, it lays out data in a particular way, like, could we explore changing that data layout to facilitate these type of SIMD loops? Yes, in fact, we have it on the roadmap, and we're going to do it. And it requires, like, vertical integration between compiler and math library and ECS and all the things. There's just been bigger fish to fry, like for for the stuff that we've been showing, like live link and stuff on the ECS. So, but yes, absolutely, and it's one of the key advantages, I think, of investing in this stack, right? There's not a lot of people who have a compiler and an ECS and all the things put together. So definitely we want to do that, and we've tried in a very limited way to do that. There's experimental containers, but I think we're going to end up dropping them, because it turns out, like, using them from mono or from IL to CPP code is just a trash fire. Like, it's so slow. So we're still exploring the best way to do that, and I think we're going to end up with some IL rewriting, because you really need to change the IL code that changes these things too, should you happen to run it on mono. And if you don't do that, like, the performance penalty, like for doing some dynamic reinterpretation and like using reflection or something, it's so slow that no one would ever want to use it. But yes, we absolutely have it on the plan. And I agree, that would be a key differentiator to make this even more accessible, right? If you already have the data laid out in like SOA packets, this is much, much easier to do. You don't have to do that input swizzling. So, yeah. Oh, so in the burst inspector, right, so you open up the inspector, so you go to the jobs menu, burst inspector, and anything that has a burst compile attribute on it, any job, you'll be able to select there. And then you click refresh disassembly, and you can set a bunch of different targets, like you can see what the code looks like for ARM and for AVX and SSE4 and stuff like that, so yeah. Cool, going once. Twice. All right, thanks everyone.